Hello class, welcome to lecture 8 with Dr. Uzuchukwu. Today we're going to learn how to measure strength in regressions. Measuring relationship strength is something that we're able to do with regression coefficients, with which we have familiarized ourselves with, from lecture 6 and 7, bivariate and multivariate regressions. And in this lecture, we're going to learn how to do it via beta weights. So the main difference here is that regression coefficients are not standardized. And so it doesn't allow us to really understand how strong a variable is with another variable compared to a different variable in that same dependent variable. Beta weights, very similar to correlation coefficients, are standardized and therefore allow us to do just that. So, and we're also going to learn about the strength of a relationship as a whole, the entire regression model, via the coefficient of determination, also known as Rsquared. All right, again, we've got our regression coefficient, our regression equation, y hat equals b naught plus b1x1 plus b2x2, and so on. And we are very familiar with that by now, yes? Okay, so we know that all these b's after b naught, which is our y-intercept, all the other b's are our regression coefficients. And these regression coefficients tell us that the x, or the independent variable, as it increases by 1 unit, the y hat, or our dependent variable, changes by that b units, that regression coefficient unit, holding constant the other variables in the model, right? So in general, the larger the coefficient, the stronger the relationship, at least when we are working with comparable independent variables. In other words, variables that have the same unit of measure, okay? But unfortunately, it's not that simple. That's why we called it unstandardized coefficients, because there are 3 main problems with regression coefficients, and we're going to look at that in the next. So the first problem that we run into with regression coefficients is that regression coefficients are expressed in units of measure, and the units may not be comparable. What does that mean? Well, we've got 1 unit of measure, as in years of service, as you can see in this example, years of service. And we've got another unit of measure, which is gender. So it's male and female. They're not comparable, right? So we can't really say 1 year of service equals going up by 1 year of service is the same as going up by 1 unit of gender, from male to female or female to male. There's no way to compare those two, okay? Another problem is units of measure that appear comparable may be less similar than they actually appear. For example, we've got years of service and years of education, right? Yes, they sound like they would be comparable because years of service and then years again, but this time of education. But think about it, right? Oftentimes we can start years of education as an employee at 12, right? That's a high school degree, diploma. We can go up to 20. That's maybe a master's degree, or actually that's a PhD. 16, that's a college degree. But with years of service, you kind of have to start at 0. Years of education, starting at 0 is not. Starting at 1 is not even really seen, right? We don't see anyone that has 1 year of education working at the federal government. We may see someone that has 1 year of service, right, working, and this is their first job, right, after college or so. So there is some discrepancy there. There are some differences, even when we're talking about years or months or whatever we may be talking about that have the same unit of measure. And then the third problem is that changing the units of measure will have a dramatic impact on regression coefficients. For example, years of service, 1 year, 12 years, 40 years, and then they retire, versus months of service. That's, 40 years times 12. Imagine. So that's a whole lot. The regression coefficient is going to be a whole lot bigger than, so 1 year of service versus 12 years of 12 months of service. Again, let me say that again. 1 year of service is the same as 12 months of service, but that regression coefficient is going to be much larger for the 12 months of service, because all we're doing is multiplying by 12 essentially. But as you can see there in red for number 3, but it does not actually change the relationship between those two variables. It's still what it is, okay? So now that we've talked about the regression coefficient and how there is some discrepancy there, and because it's not standardized, now let's look at the beta weights, which we also know in some cases as the correlation coefficient. We talked about this in lecture 5, and so or 4, I think it was 5, and so we know what correlation coefficients mean and how we can interpret them. So let's do some comparison. In regression analysis, the beta weight, or the standardized coefficient, is the average amount by which the dependent variable increases when the independent variable increases by 1 standard deviation, and the other independent variables are held constant. It's a lot of words. So the beta weight standardizes the units of measure of all of the x's, Changing the units of measurement has no impact on the value of b. So, for example, when a unit is changed from 1 year to 12 months, we know that 1 year equals 12 months. It's the same. In the case of the regression coefficient, it would change. In the case of our beta weight, R, it does not change. So beta weights don't change, okay? So interpreting the beta weight, as the independent variable increases by 1 standard deviation. And let me say that again because it's really important that we know what it's increasing by, not 1 unit, because we're not talking about it in terms of the unit of the independent variable anymore. Say we're talking about years of education. For the regression coefficient, we would say as years of education increases by 1 year, right? With beta weight, we say as years of education increases by 1 standard deviation, because all of the dependent variable, the one dependent variable is now being measured across all the independent variables, but by that 1 standard deviation, the standard deviations, okay? So as the independent variable increases by 1 standard deviation, the dependent variable changes by the beta weight standard deviation. Whatever is listed in that regression output for beta weight, that's how much the dependent variable changes by that number of standard deviations, holding all the other variables in the model constant. So the next slide demonstrates how beta weight is similar to correlation coefficients in that they are standardized. And so we can actually rank beta weights, whereas we can't do that for regression coefficients. Our example, here's our output. You can see here that our dependent variable is salary. We can see several independent variables: years of education, we see years of service, we see age, how old are you on your last birthday, we see gender represented by male, and we see a set of dummy variables: Asian, Black, Hispanic, Indian, and of course our reference group here for this set of dummy, yeah, you guessed it, is white, okay? So when we're looking at the regression coefficient, right, the regression coefficient, we should see that 1 year of education is worth $3,232.50. Okay, so each additional year of education you earn, your salary increases by about $32.32. Okay, at least in 1991 it did. And then we can go down one and we can see as your years of service increases by one, right? Your salary increases by $730. So we've got years of education at 3232. We've got years of service at 730. The unstandardized regression coefficient indicates that education has a much greater impact on expected salary than years of service. So now let's look at the beta weight. You can see in the third or fourth column over, it shows standardized coefficients, and right below it says beta. That's our beta weight column, okay? And we can see for years of education, the beta weight is 0.481. The beta weight for years of service is 0.434. Yeah? So what is that telling us? All right, so remember what I said in the the second bullet point to be exact. The unstandardized regression coefficient is telling us that education has a much greater impact, right? 3,200 versus 700. And now with the beta weight, we're seeing that they're pretty close. They're actually almost the same, 0.48, 0.43. And so let's interpret this, right, the way that we just learned how to interpret in the previous slide. As years of education and years of service increase by one standard deviation, holding all the other variables in this model constant, expected salary increases by 0.48 and 0.43 standard deviations respectively. Okay? So once these variables have been standardized using the beta weights, we can see that one standard deviation increase in service and education have almost the exact same impact on salary. Initially, based on the regression coefficient, we would say education has a much stronger impact on salary. But based on the beta weight, we can see that education and service years, your service experience are about the same. And let's try to think about that more practically now. Think about the cap of education, that you can only reach a certain cap, right? Your minimum may be 10, 11 years of education if you maybe dropped out of high school. And your cap may be, 16 is college, 2 more years, that's 18, that's master's degree. We've got another maybe 4 years, so 22 at a maximum of education. 23 maybe if it takes you 5 years to finish your PhD or so. So at most, we'll just top it off at 25. You can only have up to 25 years of education, possibly, and very few get up to that level, right? Whereas years of service, you could start working at the age of 16, 17, 18. Imagine you're 70 now, 67, 62, and you decided I want to retire, right? That's 50 plus years of years of service. And so we can see how it sort of balances itself out. And so years of service can definitely have a similar impact on salary as years of education. That was a lot. Okay. So we're able to rank order not the regression coefficients, but we are able to rank order our beta weights, just like we did with correlation coefficients. In the exact same way, we can look down that beta column and we can see which variable has the strongest relationship with salary and which has the weakest, right? We can see that years of education should have the strongest. And what do you suspect has the weakest? In this case, we see age actually has the weakest relationship at 0.008. All right, so now we're looking at the coefficient of determination. We just talked about how variables how strong the impact of a variable is to the dependent variable. But now we're going to look at the variables as a whole, all of the variables inside the one multivariate regression output. So another way to understand the strength of independent variables is to predict the dependent variable. In predicting, the dependent variable is using R-squared, coefficient of determination. This is the equation for that. This is not a class where I try to explain too much of the mathematical concepts. While it's important to understand some of these mathematical concepts, it's more important for me to you to understand the interpretation of these calculations. This is not a math class. This is not a calculus class where we have to prove all of the equations that we use. We just know that these equations have been tested and approved, tried and tested, and we just know that they are correct now. So R-squared is the proportion of the variation in the dependent variable that can be explained by the independent variable. Okay? The proportion of the variation in the dependent variable, so the independent variables are helping us understand what causes the dependent variable to go up or down, to fluctuate, to vary. What causes salary to increase versus decrease. That's what that second bullet point is really saying to us. Okay? And just like our correlation coefficient had a range of -1 to +1, our R-squared has a range of 0 to 1. There's no negatives because anything squared is always positive. And so our R-squared goes from 0, minimum, to 1, maximum. While beta compares independent variables to see which one is stronger, R-squared looks at the regression model as a whole. I said this already, but it's always good to repeat it, especially during the learning process. R-squared looks at the regression model as a whole to see the collective impact of all of the independent variables in the model. Collective impact. So, if the multivariate model perfectly explains the dependent variable, all of the observed values would be on the regression line. Usually, this is the point where I create a table or chart and show you what I mean. But I can't seem to function well with this PowerPoint and creating videos, so we're just going to have to let that one slide. Unless you're in my on-campus class. I can show it to you then. Okay, so all of the observed values would be on the regression line. If the multivariate model perfectly explains the dependent variable. What would also happen is that there would be nothing unexplained between the regression line and the observed value. And we're going to look at what that means later. And then also, it would mean that 100% of the variation in y is explained by the different independent variables in the regression. So all of the variables that we've decided to put into our regression model, if it explains perfectly the dependent variable, then our R-squared should be 100%. It should be 1. Okay? All right. So based on the equation from the last previous slide, SST is the total sum of squares from the mean. SST is the sum of squares of the actual values of y from the mean value of y. Okay, you're looking here at the equation for SST, and you can see the y1, that's our actual value. Okay, the y bar, just like with our standard deviation, we had x bar, our y bar, anything with the bar subscript, that just means mean. That's the mean, that's the average. So in calculating when the computer, because we never calculate this, okay, but this is just background information so you know how these numbers come about in Excel or SPSS or Stata or whatever software you use. This is how the computer comes up with these numbers that you ultimately see in your regression output. So to calculate the total sum of squares deviation, you use the actual values of y that you get from your surveys, right? If someone said their salary is $35,000, that's an actual value. If someone said their salary is $38.397 thousand, then that's their salary. That's the actual. Then you take all of that, every observation you had, every value you had for salary, right? You take the sum of that and you divide it by the total, right? That's the mean. And so that's what you're seeing here in this last bullet point. The regression sum of squares, or the explained sum of squares, is what is the sum of squared deviations from the predicted or the expected values of y and the mean value of y. So we already know what the mean value of y is from the last slide. It's all of the y's that we got from the survey, the actual y's, and we got the average of it, right? We got the average of say our y is salary. We got the average. So we already know what our mean value of y is. But now we want to predict our expected values, right? And so we do that with a regression equation. So the regression equation actually gives us that y hat. As you can see here in the very last bullet, y hat is what we've always been talking about. And the only way we get that y hat is through our regression. So not only do we know what the actual y is, not only do we know what the y bar is, which actually comes from the y actual, right? We know what our y hat is because it's generated from the computer output, the regression. And so that allows us to understand the explained sum of squares. Is the unexplained sum of squares, also known as the error sum of squares or residual sum of squares. And that's essentially what we don't know. We talk about what we know, we talk about what we don't know, and the total of that is the total sum of squares. And that's essentially it. And so again, in this equation, you can see at the very last bullet, we've got what we do know, our actual y. In this case, it's salary. So we get the salary from everybody. We have our y hat, which is our expected. We put it into the equation from the regression output, and that's what our y hat is. And so that allows us to understand what our sum of squared deviations is for unexplained. And so variations in the dependent variable, the better we can predict the dependent variable based on the inclusion of the right independent variables, right? The more the sum of squares explained will increase. So the more that we know about the dependent variable, the more that our SS explained, our SS regression will be, the higher it'll be. But if we can't really explain it, then our unexplained should be higher. That's all this slide is telling us. So the more we know, the higher our SS regression. The more we know, the lower our SS unexplained, our SS residual. Okay? That's it. That's all this slide is telling us. So let's try to think more practically about what we just learned, because it's important to get down to the nitty-gritty, because that's really what's key here. So which predictor, which independent variable does a better job of explaining variations in salary? So we can see two outputs here. We see at the top our dependent variable is salary, and our independent variable, or our predictor, is grade. At the bottom, we still have a dependent variable of salary, but we have an independent variable of age. Okay, so we have our sum of squares regression, which is our explained, which is what we know, right? Our sum of squares regression for grade at the top, we can see it's about 1.0, I think that's billion, because that's 9 zeros. Let me write that out. Make sure. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, that's actually 100 million. 100 million. And then the one below is 1 million. 3.4 million. So our regression above explains a lot more than our regression below. That E plus 0.7 and E plus 0.9 it's only telling us to multiply that, take the decimal place over to the right 9 times, which gives us a really large number. We probably learned that somewhere in elementary or middle school. At least for me, I did. Maybe high school, but hopefully everyone learned that in middle school for sure. So your E plus 0.9 means you take it from 1 down 9 times. You put 9 zeros in front of that 1.0. Okay? And that should give you about 100 million is our regression there. And our regression sum of squares for the age is 3.4 million. So 100 million is definitely more than 3.4 million. So we can see that grade does a better job of explaining the variation in salary. And that's what this is telling us. Okay? And then when we look down, it should at the sum of squares residual or sum of squares error, sum of squares what's the other word I use? Residual error unexplained. That should also tell us the same exact thing as what the SSR regression just told us. So we can see for grade, residual is 5.3 million. Whereas residual for age is much higher than 5.3 million because we've got we've got e to the 9th versus e to the 7th. So our residual for age is much higher, which means that we have a lot more unexplained in age. So we're saying the same thing. Whether you're looking at residual or regression, it should say the same thing. Okay? All right, so let's look at it again in a different way. This time, we're going to look at the R squared, the actual R squared now. Which independent variable does a better job of explaining salary? This is the same output, but rather than look at the sum of squares table, we're just going to look at the model summary. And we're going to look at R squared specifically. We can see that R squared is 0.95. That's 95% of the variation in grade is explained, the variation in salary is explained by this grade variable. Whereas only 3.3% of the variation in salary is explained by this age variable. So again, yet again, we see that no matter which of these numbers you look at, they should all tell you the exact same story. Whether you looked at SSR, SS regression, SS residual, or you're looking here directly at the R squared, it should all tell you the same thing, that grade explains more than age. Okay? And just take a look at the interpretations I provided here, because this is the language that we want to use whenever we're talking about R squared. Okay? Federal employees' pay grades explain 95% of the variation, whereas their age only explains 3.3% of the variation. All right. So again, our equation is here. We see that R squared equals SSR over SST. So in one of the slides, we looked at SSR and SST, and we could see all that in one table. In another table, we were able to just go straight to R squared and see that value for what it was. And so either way you look at it, you can still see the same results. If the explanation was perfect, and we're just going to do some review now because we talked about this earlier in earlier slides. If the explanation was perfect, all of the observed values would be on the regression line. There would be no unexplained variation between the regression line and the observed values. And finally, the maximum value of R squared would be 1 or 100%. Okay? If you see the number 1, that essentially means 100%. If you see the number 0.93, what does that mean? It should mean 93%, okay? So your R squareds are always going to be in decimals, right? So it goes from 0 to 1. And then if x's, or if your independent variables are completely unrelated, the regression, the R squared should be 0. It should be very close to 0. There should be no variation, no explanation whatsoever for the dependent variable based on that independent variable. And just some other pointers to know: R squared is always positive. Okay, the higher the value of R squared, the stronger the relationship between that dependent variable and all of the variables collectively in that model. In the model that we looked at in these examples, there was only one independent variable that we looked at in a model, whether it was age and salary or grade and salary. But moving forward, we're going to have several independent variables in a model. And so just know that the R squared will ultimately be talking about all of the variables collectively in that model and how much they can help explain that dependent variable. So backtracking a little bit now, in a bivariate regression like the ones we saw in this example, in these examples, R squared is actually the squared of the correlation coefficient R. We know what the correlation coefficient is. We know how to gather that information on our statistical software. And so when we get that number, if we're talking about bivariate regressions, then that R squared is essentially the same thing as that correlation coefficient squared. Simple as that. This has been a fun lecture. I hope that you have even more fun practicing what you just learned. So get to it.